Central High School is competing against Northern High School in a backgammon match. Each school has 3 players, and the contest rules require that each player play 2 games against each of the other school's players. The match takes place in 6 rounds, with 3 games played simultaneously in each round. In how many different ways can the match be scheduled? Now, to keep organized, let's define variables for each player. Not variables in the conventional sense, but symbols. So for Central High School, call the players ABC, and for Northern, call them D, E, F. Now, we're going to need to get organized, so we come up with a sort of table diagram. Now, we know that for every pair, we need to have each pair twice, since each player must play 2 games against each of the other school's players. And since 3 games take place simultaneously, everyone is playing. I mean, consider this case. That's 3 games and everyone's playing, and every other possible arrangement results in every single person playing. So a nice way to start is, without loss of generality, just fix the order of A. Right? Just fix D, D, E, E, F, F, and then we can permute later. And the number of ways to order A's games is the number of ways to order the letters in the word D, D, E, E, F, F, which is a very common problem. It's just 6 factorial divided by 2 factorial times 2 factorial times 2 factorial, which is 90. 720 divided by 8 is 90. This is a very common problem, and just by a well-known algorithm and idea, we get 90. Now we need to split this up into cases. Now let's consider the easiest case first. What if B plays E here and plays E again? Well, then clearly this is defined as F. I mean, there's nobody else C can play. But what else? We would have, for the AF case, since F is taken, we would necessarily have, sorry, not G. Since F is taken and E is taken, B would have to play D here, and would also have to play F here. So if B plays the same person as A plays the same 2 people, so if AD, AD, BE, BE, for instance, happens, or some symmetric organization similar to this one, we would only have one possible arrangement. Once B plays these 2, all the other arrangements are determined. So for this to happen, we have 2 possible ways, since B could either play E or B could play F twice. So there are 2 ways for that to happen. And now for the more complicated case, where B plays E here and B plays F here. Now if this happens, then clearly this is determined, since we only have one person left. But for the next case, we need to do even more casework. So there are 2 choices here, 2 choices for the ordering of those. And we have 2 more choices here. And to show that, we could either go D, F, or FD. Now, after doing this, the setup is essentially determined, because then we would have D there or E there. Oh, sorry, it's actually not quite determined. I misspoke there. It's almost determined. We have 2 choices here, 2 choices for this ordering and 2 choices for that ordering. Just made a bit of a mistake there, misspoke. But hopefully the idea is clear. So in the second case, we have 2 cubed contributing factors, contributing cases, and multiplying this by the original result of 90 gives us 90 times 90 times 10, with 8 plus 2, 10, yielding 900 as our total answer, E.